Very well. The title of my presentation is a semi-analytical solution for the dynamic analysis of a rectangular viscoelastic plate subjected to a moving inertial load. For introduction, it should be noted that structures subjected to moving loads cover a wide spectrum, from bridges and vehicle roads to aircraft landing runways and rotating restaurants. All of these structures exemplify scenarios where the impact of moving loads is a crucial design consideration. Historically, accounting for the impact of moving loads in structural design dates back to 1847. In that year, the D railway bridge in Chester, England, collapsed due to a train passing over it, resulting in casualties. The published technical report on the accident revealed that the impact force arising from the dynamic nature of the train load had not been considered in the bridge's design, which led to its collapse. From that point onward, designers in England were required to consider the impact of moving loads in all railway bridge designs. In general, there are two approaches for considering the effects of moving loads, known as the moving force, or shortly MF. Assume that an object of mass m is moving with a constant velocity v on a beam-type structure. In the first approach, only the effect of the object's weight, that is mg, is considered in the loading, as you can see. However, in the second approach, in addition to the weight term corresponding to the inertial effect of the mass is also included in the load. Here, W represents the vertical deformation of the beam. The effect of moving loads has been studied on various types of elastic structures, including straight and curved beams, cables, half spaces, and elastic plates. It is important to note that, as Bajer demonstrated in 2012, conventional numerical methods for structural analysis, such as FEM, cannot be used to solve the moving mass problem and account for the additional acceleration terms, especially when the object moves at high speeds, leading to unrealistic results. Therefore, semi-analytical methods are employed to solve the problem. We mentioned that the effect of the moving mass has been widely studied in elastic structures, but many of the materials we encounter in engineering, such as concrete, asphalt, plastic, and ice, exhibit viscoelastic properties. That is, as shown on this slide, the stress depends not only on strain, but also on the strain rate. Our goal is to introduce a semi-analytical method that can readily solve the problem of the vibration of a viscoelastic plate subjected to a moving mass. Well, the assumptions employed in this formulation are: one, the plate is considered thin, and we have used Kirchhoff's place theory for the plate relations. The mass always remains in contact with the plate and does not detach from it. And three, the horizontal forces between the mass and the plate are not coupled with the vertical vibrations. A schematic of the problem under investigation is shown on this slide. We have a rectangular plate with dimensions A and B, made of a viscoelastic material, and an object with mass m moving along an arbitrary parametric path defined by the general equations x0 and y0 as functions of time t. The boundary conditions of the plate are arbitrary, and the plate is supported by foundation with uniform stiffness K and constant damping C. The thickness of the plate is constant equal to H. Well, if I want to skip this systematically, explain the formulation of our problem, I must state that, like every continuum mechanics problem, we need to formulate three categories of equations: constitutive relations, strain displacement relations, and equilibrium equations. I will now briefly explain in each category in the context of our particular problem. Well, the constitutive relation for linear viscoelastic materials considered isotropic can generally be expressed in the form of a convolution or Volterra integral, as shown on this slide, where R sub ijkl is the element of the fourth order relaxation tensor, representing the contribution of the strain rate, and R0 and R1 are relaxation functions. Here, the spring damper configurations for some common viscoelastic models, such as the Kelvin, Maxwell, and Thomson models are presented along with the corresponding form of the R1 function for each one. Since we have assumed that our plate is thin, we use Kirchhoff's hypothesis to write the compatibility equations. Furthermore, the equilibrium equation for a differential element of the plate is given in this form as shown on this slide. The primary load due to the moving mass, that is Q sub m, is defined such that, as you can see, to include not only the weight of the object, but also the inertial term. The acceleration to proceed, we take the Laplace transform of the equilibrium relation, which we have repeated here for simplicity. This Laplace transform can unlock the problem, and you can see that we have the moment stress equilibrium equations and the constitutive equation. By simplifying this equation, we obtain the general differential equation for viscoelastic plates in the Laplace domain. The carets also denote the Laplace transform with respect to the time variable. We solve the equation using a discretization method by expanding the unknown function in terms of eigenfunctions. After substituting this series into the differential equation and further simplifying, we obtain the discretized equation in the Laplace domain. In order to demonstrate how this solution method works, we discretize the problem for a plate made of a Maxwell material using this approach. In the Maxwell model, the spring and damper are arranged in series, a configuration used for modeling materials such as ice. For example, in this figure, we present a case corresponding to a railway line built on ice in the Dnieper region of Russia near the North Pole. After applying the inverse Laplace transform to the equation, we arrive at a system of second-order differential equations with variable coefficients. Matrices pertain to the Maxwell model. In these relations, the auxiliary function psi, as you can see, appear during the inverse transformation process, and tau is the time of relaxation. This equation can be readily solved using appropriate numerical methods to obtain the solution. We perform the same procedure for the Kelvin model, as you can see, with a parallel spring and damper. This model is widely used for concrete and asphalt pavements. By replicating the aforementioned operations, we obtain a similar matrix formulation in the time domain where the subscript Kelvin model. Due to the large size of these matrices, their elements are not shown here. To demonstrate the capability of the solution method, we have parametrically solved 3 different examples using this approach, the specifications of which are shown in the table on the left-hand side. The remaining constant plate specifications, such as length, width, thickness, and so on, are presented in the table on the right-hand side. In our first example, a mass moves along a straight path, as you can see on the line y0 equals b half at a constant speed v0. Our material is of the Kelvin type. In order to present the results in a simpler form, we have defined dimensionless parameters for each of the variables in the problem. As you can see, gamma represents the mass ratio, that is ratio of the moving mass to the mass of the plate. S is the non-dimensional velocity. H, non-dimensional viscosity, defined so that S times H equals tau over T0, where T0 is the time that it takes for the mass to leave the plate. Kappa, non-dimensional foundation stiffness. Psi, non-dimensional foundation damping. Theta, non-dimensional time, defined such that S times theta becomes the ratio of the traveled distance to the length of the plate. And delta is the dynamic amplification factor. Using our proposed solution method, we plotted the delta spectrum versus the dimensionless speed S for mass ratios ranging from 0.1, as you can see, to 0.7. The solid curves correspond to the MM method and the dash curve to the MF method. In these plots, we vary the dimensionless viscosity H from 0, representing very low viscosity, shown in black, to 0.01, representing very high viscosity, shown in green. For context, a near zero viscosity applies to materials such as mild steel. High temperature asphalt has a viscosity around 10 to the minus 5, concrete pavements around 10 to the minus 4. As you can see, typical asphalt pavements around 10 to the minus 3, and layered damper material around 10 to the minus 2. We observe, as observed, at low speeds for all mass ratios, the delta value remains close to 1, indicating that the dynamic effects are negligible. However, as the speed increases, these dynamic effects become more pronounced. Moreover, with increasing mass ratio gamma and speed s, the proposed method effectively captures the inertial effects of the moving mass. Well, as can be seen, the accurate result carries to approximately 3.5 times the MF solution when the mass ratio is around 0.7. Furthermore, when the viscosity increases, say to H equals 0.01, there is practically no difference between the two solution methods. This is as expected, since higher viscosity significantly diminishes the dynamic effect of the mass inertia, a phenomenon that our solution predicts successfully. Another interesting aspect is the delay or lag in the plate's response. However, due to the time limitation, I have to bypass this topic. Here are the lag response results. Additionally, there are other interesting discussions, including contribution of higher modes, occurrence of the beating phenomenon, and modal interaction, which have been discussed in the article shown below, and you might want to refer to it to find out more. Well, let's see. On this slide, we examine an example concerning circular motion, where mass rotates on the plate at a constant angular velocity, omega. Let me check if this video is working properly. Yes. In this video, we present the solution results for a plate with H equals 0.001 and ratio R over A equals 0.25. Other specifications are also shown on this slide, as you can see. Well, you can see that the plate is vibrating under the excitation of a moving mass rotating around the center of the plate. Well, let me go to the next slide. On the next slide, the viscosity is increased tenfold, as you can see, while all other parameters remain unchanged. As expected, the amplitude of the plate decreases, which is consistent with our intuition and demonstrates that the proposed solution can effectively capture the effect of viscosity. It should be mentioned that the no foundation case is examined here in this example. Well, okay, here we examine the third example where the plate's boundary conditions are such that three edges are clamped while one edge is simply supported and the moving mass follows a winding trajectory. The plate's material is also modeled as Maxwell. The trajectory equation is shown on this slide. In this video, the plate's response to the mass excitation, as you can see, is demonstrated. The plate is placed on an elastic foundation. And you can find the specifications of the plate right below this video. Well, the solution method can be generalized to scenarios with two or more moving masses on the plate, as you can see from the analogous equations. On this slide, the response of the plate to the excitations from two moving masses moving in opposite directions is demonstrated. Given the nonlinearity of this phenomenon, well, the principle of superposition cannot be used. As you can see, the exact solution yields a 42% higher response compared to the solution obtained by applying superposition. For validation of our method, the problem was solved once again using the MLS method, the moving least square method, which is a meshless approach. To formulate the problem with MLS, we wrote the Lagrange equations and discretized them within the MLS framework. The results of the two methods differed by a maximum of 9%, as you can see. Notably, our method produced this diagram in under 1 minute, whereas the MLS method took 3 months, demonstrating the significantly lower computational cost of our proposed approach. Okay, to sum up, the proposed method of solution can be readily applied to solve problems involving various types of linear viscoelastic models for the plate material, various types of boundary conditions and mass trajectories, multiple moving objects. Also, application of the more accurate moving mass method is inevitable when the mass ratio is greater than 0.5 and velocity is greater than about 150 kilometers per hour, and the viscosity is less than 10 to the minus 4. Moreover, application of the approximate MF method is quite reliable when the mass ratio is less than 0.3 and the viscosity is greater than 10 to the minus 3. For most engineering purposes, considering only the first 20 modes in the proposed method gives accurate and reliable results. The lag spectra were well described through introduction of parameter S times H. And finally, the proposed Laplace transform method introduced here could be readily applied to solve a broad range of vibration problems concerned with viscoelastic plates, beams, and more generally structures. And finally, thank you for your attention. If you have any questions, please feel free to ask.